3s1 orbital. Now, the elements at the periodic table can also be classified into metals, nonmetals, and metalloids. And in the left side of the slide, you can see the descriptions that corresponds to each of those classifications. Do you need to know how they are either metals, nonmetals, and metalloids? Sure. And even though at first it may look overwhelming, it is not as hard as it may look. What I encourage my students to do is just to know which elements are metalloids. Because once you know the ones that are metalloids, to the right of the metalloids, including hydrogen, which is right here, all of those are nonmetals. Anything to the left of the metalloids are all metal elements, and that is the end of the story. This is important along with electron configurations because it allows us to understand why is it that when some elements come together, they either make ionic compounds or covalent compounds. An ionic compound, which is what we have on the left side of the slide, are going to form because of the transfer of electrons. They tend to be solid at room temperature and they have high melting points. But when we need to identify if a particular pair of elements are going to make an ionic compound versus a covalent compound, what we're going to pay attention to is their classification. So when we have a metal combining with a non-metal, we see that that's what forms an ionic compound. Because when we pay close attention to what's happening at the atomic level, metals would lose electrons and gives them to the non-metals. As a result, the metals are going to be positively charged and the non-metals are going to be negatively charged. And that's what forms an ionic bond. The ionic bond is not a line that we draw between the two atoms. It is basically the electrostatic interaction between having something that is positive and something that is negative because of the transfer of electrons. On the other hand, when we have covalent compounds, they share electrons. These compounds tend to be soft and flexible, and they have relatively low melting points and boiling points when we compare them to ionic compounds. Now, how do we know if a pair of elements are going to make a covalent compound, which are also known as molecular compounds? Well, we're going to have a non-metal combined with a non-metal, and they're going to share electrons and they're going to form a covalent bond. That covalent bond is right here, is the two electrons that are going to be shared, two or more. In this case, we're only illustrating two, that are going to be shared between those two non-metal elements. That's what forms a covalent compound. Now, also note that there has been examples of metalloids plus non-metals that make covalent compounds. And actually the majority of the metalloids, when they're combined with non-metals, they make covalent compounds. To date, I have never seen examples of a metal combining with a metalloid. So that's why I only talk about metalloids with non-metals forming covalent compounds. So let's practice identifying what kind of compound are we going to generate depending on the combination of elements that we have. Here we have a list of pairs of elements and we need to determine if they form an ionic compound, and we're going to label it with a capital I, or if they form a covalent compound, which we're going to label with a letter C. So I'm going to do problems A, B, and C to illustrate how to identify this. So first we look at oxygen and chlorine. When I look at the classification of oxygen and chlorine, when you look at the periodic table, they are both to the right of the metalloids. So what that means is that they are both nonmetals. If you have two nonmetals, that makes a covalent compound. Let's look at the next one. Hydrogen and hydrogen. Hydrogen is a non-metal element, and if we have two of them making a compound, that also makes a covalent compound. Let's move to the last pair. Oxygen is also to the right of the metalloids, so that is a non-metal. Now, magnesium is to the left of the metalloids. So that makes it a metal. And because here the combination is metal and non-metal, then that's going to make an ionic compound. Make sure that you practice. Now, let's understand more in depth why is it that these metals want to lose electrons and why these non-metals want to gain the electrons that have been lost by the metals. And that's because they form those charged species that I introduced a few moments ago. Now, let's give name to those charged species. So as I mentioned, metals are going to be losing electrons. And they're going to form a charged ion that is positively charged. That's what we know as a cation. So, if we look at the electron configurations of the atom before losing the electron, this is what it will be for the example that we have, which is sodium. Sodium at ground state, because it has 11 electrons, is going to have the electron configuration 1s2, 2s2, 2p6, 3s1. Now, it's going to lose one valence electron, and now it's going to have 10 electrons as a cation. So, when we write the electron configuration of those 10 electrons, then that means that this becomes 1s2, 2s2, 2p6. By exploring the periodic table, we will notice that this electron configuration also corresponds to a noble gas, specifically neon. So if we put the noble gas configuration, then we know, wait a minute, sodium lost its valence electron because the 3s1 electron is in the outermost shell for sodium, and it became electronically a noble gas. Why is that advantageous? As we discussed previously, remember that having a full valence shell gives you stability. So metals are willing to lose their valence electrons, either 1, 2, or 3, in order for them to just gain specifically the electron configuration of a noble gas. So what happens in the case of a non-metal? In the case of non-metals, they are always going to be accepting those electrons that are lost by the metals. And we are going to look here at the example of chlorine. The electron configuration of chlorine goes as follows. 1s2, and this is at ground state. 2s2, 2p6, 3s2, 3p5. It is known that, as you can see by the arrow, that chlorine is going to accept one electron. Now it goes from 17 electrons with this electron configuration to 18 electrons with the following electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. So when that occurs, then all of a sudden, chlorine is going to have a full valence shell. Because now, at level 3, it has 8 electrons. When we pay close attention to the periodic table of who shares that electron configuration that now chlorine has when it formed that negatively charged ion that we know those as anions, well, it will look like argon. So when we look overall of how ionic compounds are formed, it's because the metals lose electrons to now have an electron configuration that is similar to a noble gas, and non-metals do the same but by a different process. They're going to do it by gaining those electrons at the outermost shell to also have a full valence shell, but in their case, they're going to be negatively charged. So you may be wondering how many electrons need to be lost by the metals, or how many electrons need to be gained by the nonmetals. In the following table, we have illustrated that the group number in the periodic table can also give us an insight to that. Because, as you can see towards the left of this image, we can see how metals are going to lose valence electrons. The metals that are in 1A are always going to lose one electron. That's why they become +1 charge. When it comes to the 2A elements, as you can see, they lose 2 valence electrons. That's why they become 2+. And when it comes to the elements in 3A, aluminum is a metal, so that's why it's going to lose 3 electrons. Remember that this rule in 3A doesn't apply to boron, because boron is a metalloid. And as I talked about before, metalloids will be making covalent compounds, so it's not involved in this whole making specifically ionic compounds. Now, when it comes to the nonmetals, how many electrons do they really gain? Well, in the case of the elements in 5A, they have to gain 3 electrons. That's why you see nitrogen with a -3, phosphorus with a -3. In the case of anybody in 6A, oxygen is going to gain 2 electrons. That's why you see it as O2-. Also sulfur 2-. Any of the elements in 7A, meaning your halogens, they all only have to gain 1 valence electron, okay? And you can see that at the corners, the arrows are going to be pointing at after, in the case of metals, they lose an electron. The arrow is going to point at the noble gas that their electrons remaining are going to look like. And in the blue area, we have the designations for the metals. In the yellow area, we have the designations for the noble gases. Or the noble gases for the nonmetals, sorry. Now, in the periodic table, we also have elements that will be forming cations, but that they have variable charges. And when it comes to that, understand that there is a selected list of elements that can do this, but I'm just going to summarize it for you. As long as you have elements in group B, they are going to form one or more cations. So transition metals or transition elements are going to form multiple charges. Along with those, there are 4 elements that are outside group B that also do the same. Those are tin, antimony, lead, and bismuth. They also form cations of multiple charges. Now, it is important to note that out of group B, there are 3 elements that can only form one type of cation, and that is zinc, cadmium, and silver. Zinc can only form the cation +2. Cadmium can only form the cation +2. Silver can only form the cation +1. So, how do you know that they form these? Well, because typically elements that have variable charges, we put in parentheses a Roman numeral to designate the charge that they have at that moment.